Hello everyone. In this video I'm going to be talking with you about the operation of electromechanical relays. So to begin with, what is an electromechanical relay? Well, it has two parts to it, which is why they make the name of it such a large name there, electromechanical. It has an electricity side and then it has a mechanical side. And so to begin that discussion, we'll start off with, well, what is a switch? Because ultimately, this is really what it boils down to, is that it's really a type of switch. So for your normal switch that you have on your wall outlet, okay, you have what we call a single pole, single throw switch. And that single pole, single throw switch, when you switch it closed, it stays that way. When you switch it open, it stays that way. And that's just the basic function of it. There's usually, well, there's always some kind of a power source there. And let's say like you have your light bulb, and then that light bulb will come on based upon the fact that you've supplied it with current by closing that switch and completing the circuit. Okay, so that's your single pole, single throw. Now, there's some key points to just go over to begin with about electromechanical relays that give it an advantage over the single pole, single throw ordinary switch that you would find like on your wall. Okay, first, they physically and electrically isolate the input from the output, where this ordinary switch, single pole, single throw, do not provide isolation and create a potential safety hazard. Now, they've done an excellent job with these wall switches where they have put or made the lever out of plastic, and plastic is an insulator, okay, at least for the voltage levels that we work with. They're an insulator. And so it erases the possibility, eliminates the possibility that you would receive a shock by touching only the lever. In addition to that, they also ground the circuit so that if there's some kind of a mechanical fault with it, it will conduct enough electricity to set off a circuit breaker and trip it. Okay, so there's a lot that has gone into it, but with the electromechanical relay, it's guaranteed that you are isolated from it. So you will definitely encounter electromechanical relays in systems where you have very, very high voltage levels that could be hazardous to the person. It's the ultimate way to isolate somebody from some kind of a hazardous level of power that you're trying to turn on and off. So that's number one advantage. Number two, the user is able to use a relatively small amount of electricity to control a relatively large amount of electricity. Okay, so again, that really ties into the isolation advantage. You'll use a small amount of electricity, a small signal, and then you can control a relatively large signal. When it comes to semiconductor technology and transistors, you call that amplification. So it's like amplifying your efforts, okay? And so that's the second advantage. The wall switch is really not amplifying your effort. You're just pretty much in the middle of it. So there's really no amplification factor there. So that would be number two. Number three, by configuring a relay with feedback, you accomplish what they call a seal-in function. That's the industry term for it, seal-in logic or seal-in function. And it can be made where it will hold itself on after an input turns on. This is used frequently in ladder logic programs where the symbols are relay contacts and coils. So you'll just give it feedback, and let's say like you had a single pole, single throw switch, and you put it on and then you turned it off. after you release this and you took it from off, then it would still stay on, because that type of a configuration you would say has memory. And then you'd have another single pole, single throw, where you use that in order to reset the circuit and turn it off. So you'd need two of those in that case. But it's a circuit where you would say that the circuit has memory, where it would stay on. Okay. So next, let's go into a little bit of physics on electricity itself to better understand how electromechanical relay will work. Now, if we have a circuit where we have a source and then really we don't even have a load, but we just have our load is going to be our wire, and we just have a source, and that is this is a closed circuit. Anytime current passes through a wire, it creates a magnetic field around it. So you have this magnetic field going around it, and it's in what they call concentric circles, lines of force there. Now, it has no definite north or south pole with those lines of force, but the fact of the matter is that you do have a magnetic field that forms anytime you have current going through a wire. For the most part, it's either undetectable or it doesn't do anything to anything else, but it is a matter of the physics of electricity and current flow. Now, what is interesting is that if you have that same circuit and you were to coil up the wire and coil up that wire substantially to the point that you concentrated these lines more, that field would be stronger. And when it does get that strong, you have a north and a south pole. Now I'm using the conventional current flow model here, where it's movement of holes. So we're going from positive to negative. The real deal of the whole thing is that electrons actually move. That's called the electron current flow theory, which is what physicists actually use. Electrical engineers stick to the conventional current flow model, which just says that the holes move. And when that happens, then this is the orientation of the field as it goes in this way. Okay, so that's just a little extra side knowledge there. But the point to make here is that you have this field that forms here with a definite north and a definite south. And so what actually concentrates that and makes it stronger is if you put a bar into the middle of it. Say like you have these big loops, just so you can see that I'm putting a bar in the middle. If I put an iron bar there, what happens is that field becomes more concentrated. Now that's another physical phenomenon that's due to the fact that it has a greater ability to support the formation of magnetic field lines, and they call that permeability. But the important point to remember just in the scope of this discussion is that you have that iron bar there so that you can concentrate the lines more and make it stronger. So it's more useful when you deliberately make it so that you're trying to generate a magnetic field. Okay, so that's your iron bar. Now, moving on here. This area of electromagnetism is very interesting, and we do need to understand this, but this is background information. And so we'll get back more into our discussion exclusively on electromechanical relays. So relays in a circuit. So when we have a circuit here and we have our single pole, single throw switch, okay, SPST, T, single pole, single throw. That's the acronym. And let's say we have this sort of a deal here. We have a bar there. That bar is actually in the middle, but schematically they usually draw it like that. It's a lot easier. I think that's where it comes from. And let's say we have a low level voltage here. This will be a DC voltage, and let's say it's like 12 volts. Okay. Suppose we wanted to close the contacts of something. Okay, so we're going to close those contacts. Over here we have a whole lot of voltage. Say we had like a light bulb that we want to power on. And we have 120 volts AC connected to it. Okay, now if we took this, turned it on, and we had this magnetic field here, it would tend to pull this closed, and in fact, if it's substantial enough, it will pull it closed. So we say that it's magnetically coupled. Okay, so this is the electrical part. Okay, electrical part, and then this is the mechanical part. The mechanical part is that switch being pulled closed. So when you close that switch, then you complete the circuit, and then now you have your light bulb that is able to be energized by your 120 volt AC. Then when we let go of the switch, what happens? Well, this is usually spring loaded, and it'll go back to a default position. When that happens, then the switch will open back up. We call this a normally open contact. So that would be your normally open contact. It just says that by default it's normally open, and that's usually physically possible or made to be that way based off the fact that it's usually a spring. Okay, so it's usually spring loaded, and when you're not energizing this circuit, it's normally open. Okay, and that's what relays have on them. They have usually like two contacts, a normally open and a normally closed, but they're spring loaded so that you have a default position for either one that you want to use depending on your application. Okay, so that's overall basically the operation of your relay. And so what we can go ahead and move on to is a couple of applications. So for our applications here, we just went over this, and that's our first application. Okay, this circuit itself, which is usually the main, whole main application that you normally find them in. Okay, now there's a second application. Say for instance, I had this circuit, and for some reason, say this wasn't a light bulb. Say this was something that was a little bit more, it had to be like a safety measure of some sort. Say like it was a motor, right? And if that motor doesn't need to come on until a certain amount of time after I have operated a switch, usually that's like could be a push button switch. It just depends. Or it could be your single pole, single throw switch. Let's go ahead and just stick to that for now, just to keep this simple. And so you have your single pole, single throw switch. If you do not want something to happen immediately, and you want a time delay of some sort, then what you would buy is you would buy a relay that has a time delay function built into it. So they have a special type of relay that has a time delay built into it, so that a certain amount of time has to expire before this is connected into the circuit before you have a completed circuit on this end of it, and then this gets closed. Why in the world would you want to do that? Well, maybe perhaps you might want to give yourself some time before a process happens. Say maybe you want to have a process where you close a gate or something like that. Like let's say you're driving, like somebody is a security guard or something like that, and then they hit close, but they need time in order to drive their car out of the facility before the gate actually starts to close. Kind of like a garage door opener or closer or whatever. Then you would use a time delay relay in that instance, okay? And this motor would be connected to, say, maybe like the door, okay? So that would be your time delay function of a relay, and that is one application of it. Now, there's another application that I think by far is a lot more common, and really where the relay has its own niche, where pretty much nothing else is going to take the place of that. And that is that relays can be used to close multiple contacts. So this will be our last circuit that I draw here to make a point about this. And so for application, that is. And so let's say you're dealing with really big voltage, L1, L2, and L3, three-phase voltage in the amount of 460 volts AC, and that would be RMS. So it's actually even bigger than that. This is industrial level voltage. It's not available at your house, but it is available at companies. Companies do have access to 460 volts AC. So that's pretty big. It's multiples of times, it's a few times bigger than what is coming out of your outlet, and you definitely wouldn't want to be in contact with what's coming out of your outlet in your house, your residential electricity. You wouldn't want to be in contact directly with that, touching it, and definitely, if that's the case, you wouldn't want to be in contact with 400 volts, 460 volts AC RMS. And for the most part, that's usually a minimum. You can see on certain drawings that it's as high as like 480 volts. But most of the time, people note it as being 460. Okay, so you definitely don't want to be in contact with that. And it's three-phase, so you're going to have to switch off or on three phases, right? So with that being the case, you want to be isolated from it. And the most common thing that uses 460 volts AC, RMS that is a motor, okay, to do mechanical work, going from electrical energy to mechanical energy. All right, now without putting in more detail, you have overloads that, if this motor draws too much current, will open up, but just for the purposes of keeping it simple, we'll just make it very, keep the simplicity going here, and we won't draw those in. But there's usually a little bit more to it than that. Now, these single pole, single throw switches, they're usually represented whenever you see relay contacts. It looks like that, but I'm just going to keep it simple and stay consistent with what I've been drawing up to this point. So long as you know what it is and what it means, that's really what's important. So you'll have, say, like your coil over here. Actually, let me draw this a little bit more lower because I want my bar here, and then I'll have my coil, and then I'll have my circuit over here. Should have drew it more like here, running out of space. But anyways, so I have my circuit here. Ground, and and this is VDC, perhaps in the amount of 24 volts. It's very common. And we'll give this a reference designator, switch 1. And then the dashes only indicate that it's magnetically coupled or magnetically linked. And so when we hit the switch here, then this relay will close all these contacts together. And when you have a situation like this where it closes a bunch of, a couple of like a few, which is 3, okay, so like a few very high powered contacts to contact and make contacts for a motor, they usually call that type of a relay a contactor. Okay, so this is industry language here, terminology here. It's called a contactor. And so that would be your third, pretty much most common application of an electromechanical relay. And so with that being said, that is all that I will be covering in this particular lecture on electromechanical relay. So you might want to ask yourself, what do these things actually look like? Is there a physical representation? Like, what does it physically look like? Well, there is a physical representation of it, and this is what it looks like. This happens to be one, and so this is what the physical form of it looks like. And so with that being said, that completes this lecture. So thank you for watching and have a nice day.